Okay, let's talk about spatial analysis. Spatial analysis can be thought of as similar to statistical analysis, but includes a 2D coordinate plane. Assumptions of statistical analysis, such as normality, homogeneity, linearity, and independence, are not valid here. Spatial analysis describes the steps we undertake to convert raw spatial data into useful information, aka we add value by doing transformations, which brings out patterns and anomalies. In this class, we'll talk about 3 types of analysis: measuring, spatial joins, and finding center in 3 different videos. There's a lot more though, and I encourage you to take our more advanced spatial analysis and geographical analysis courses in our department. So let's talk about measuring distance. First, we have Euclidean distance, or straight line distance, also called Pythagorean distance, or as the crow flies. It's got a lot of names. This is fairly easy to calculate and relies on a projected coordinate system. It has a couple drawbacks though. It doesn't include topography, the Earth's curvature, or a road network, for instance. This means that it's good for short distances where we don't have to take into account the Earth's curvature, or where we just want to know the basic distance between 2 points, not say how far you have to walk or drive, for instance. Next, we have Manhattan distance. The name of this comes from the grid-like street geography of Manhattan, New York. Here, we aren't using Pythagorean distance or straight line distance. This is the sum of the horizontal or vertical distances between 2 points on a grid. In the image on the right, you can think of this as the orange dots here, the blue dashed line here, or the solid red line here. All give you the same distance, but follow different routes. Notice that the dot dash green line, that's the Euclidean distance shown for comparison. Next, we have great circles, or geodesic distance. This is the shortest line on a globe. On this projection, it looks like a curved line, but in fact, this is the straight line and shortest line between these paths. Remember, projections always distort something. If you held a string from Seattle to Bangalore, India, shown on this map, the line shown here on a globe would be the shortest path between these 2 places. In this way, this type of distance accounts for the Earth's curvature. Finally, we have network distance. Remember how Euclidean distance is just the straight line path, or as the crow flies distance? Well, network distance gives you the distance following a network. Perhaps this is following the street network, like you would need for getting directions or distance driving your car. Or like here, where I used the bike network. This network distance shows me that to ride from my office in Condon Hall, following the bike network, it is actually 4 miles to get me to the Springfield Public Library. But as you can see on the map, it doesn't look like the most direct route, but it's the safest and easiest on a bike, which is why Google gives it to me as my route. As you might be able to imagine, network distance is the holy grail of online navigational maps. Next up, let's talk about measurement of areas. One of the things we often want to do is measure the area of a polygon. This is the measurement of the space in 2-dimensional projected space. This is given to the user in the same units as the coordinates. So make sure you're using a projection which uses coordinates that you can use. Maybe something like meters. So you would get square meters, or feet, and you would get square feet. For instance, it won't be very helpful or possible to get the area of a polygon in decimal degrees. Why? Because that area actually changes depending on your latitude. Also, make sure to be aware of projection distortion. Next up, we can also measure the perimeter of an area, which is really just the length of a line, since polygons are just a set of closed polylines. This can include the perimeter of donut holes, such as here in Lesotho, which is inside South Africa. Finally, we can also measure something called the compactness of a polygon. This is used a lot in gerrymandering cases. Side note, I would argue this isn't the only important spatial issue related to gerrymandering, and compactness isn't always an indication of whether a district is gerrymandered. However, compactness is generally measured by assessing the relationship between the perimeter and the area and understanding that relationship.